All right, thank you very much for the introduction. So today I'll discuss our recent work on leveraging foundation models to boost the simulation capabilities for physical AI systems broadly, with a focus on autonomous vehicle applications. Now, the premise of this talk is that foundation models provide key opportunities to dramatically increase the development of robotic systems and autonomous vehicles in particular. And to be more specific here by a foundation model, I mean a model that is being trained on broad data, typically at internet scale and in a self-supervised fashion, and that can be adapted to a wide range of use cases or downstream tasks. Typical examples of foundation models include large language models, vision language models, video generation models. NVIDIA actually has on its website a catalog of foundation models you can play with. Now, we're not yet at the level where we can train one massive model and consume any data modality, but this idea of pre-training on very broad data and then fine-tuning on specific tasks has been proven very useful in a variety of different domains, to the point that oftentimes when we play with these models, we're left with the exclamation, wow, I didn't even know that the model could do that. So the key reason why foundation models also hold a great promise for accelerating robotics development is that they provide an opportunity to tap into generalist knowledge that is provided at the internet scale. And to fully appreciate this point, it's useful to make a parallelism with how humans learn to drive and actually drive. We as humans bring a lifetime of general experiences to the task of driving. And this large pool of experiences is very important in order to have enough contextual and semantic understanding to reason about difficult cases, corner cases. Analogously, the hypothesis is that foundation models, which have been trained on both data from the driving domain and crucially also from the non-driving domains, provided an opportunity to bring lifetimes of generalist experiences to the task of driving. At least this is the hypothesis. The question then is, how can we access this generalist experience as part of a robotics development program? And the answer is in multiple ways. Indeed, foundation models can empower several aspects of an AV or robotics development program, all the way from offline development processes, such as, for example, auto-labeling and simulation, all the way to the onboard stack, either by enabling new autonomy stacks or complementing existing, more classical autonomy stacks. So what I'll do today is to discuss in more detail how foundation models provide opportunities to boost our simulation capabilities. In general, simulation has always been the holy grail for robotics. If we had like a perfect simulator, robotics development would be dramatically accelerated. And indeed, in the past couple of years, there have been significant advances. In particular, in the past couple of years, neural field representations such as nerves have emerged as an extremely powerful tool for scene reconstruction and representation. As shown in this video, our recent work, Nerve, can decompose a complex scene into its static background, dynamic objects, and even an estimated scene flow, all through self-supervision, that is, without any human annotation. And with such a scene representation tool that is geometrically accurate, one can now simulate sensor data in a highly realistic fashion, such as these resimulated multi-view RGB videos capturing novel, unseen viewpoints. And one can also simulate other sensor modalities, such as, for example, LiDAR point clouds. Now, this is great, but a caveat here is that all the agents in the scene are being replayed. So basically, they do not interact with the behavior of the ego vehicle, so the policy that you're trying to test. So to fully close the loop in simulation, in my group, we have done a lot of research on developing traffic simulation models or behavioral simulation model, pushing the state of the art in terms of realism, diversity, and controllability. So as I said, our latest work in the area of traffic simulation models is represented by CAT-K, that is going to be presented in the next couple of weeks at CVPR. So CAT-K core innovation is a balance of open loop and a closed loop training for traffic models. It rolls out the policy in a closed loop while biasing sampling so that the resulting trajectory stays close to the ground truth trajectory, thereby enabling the use of ground truth supervision losses as in open loop imitation learning, but without encountering the traditional challenges of closed loop training. So this is a very strong performance, enabling a 7 million parameter model to significantly outperform its larger 100 million counterpart, topping the Waymo OpenSim Agent Challenge leaderboard in 2024. So while we're now in a position to produce a high fidelity simulation from a sensor simulation standpoint, from a sensor realism standpoint, and from a behavioral realism standpoint, there is still a significant challenge, that of generating scenarios that are indeed useful for testing a policy that has been developed. It's easy to generate data. Generating data that is useful is much, much harder. So this is a setting where foundation models can boost our existing capabilities. Specifically, we have explored how large language models can enable an intuitive interface to control the generation of simulation scenarios. With our recent work, LCT Gen, we are able to not only control the evolution, but also the initialization of a simulation scenario via natural language descriptions. In short, LCT Gen works by first converting a text prompt into a structured representation, which is then used as an input to a map retrieval framework to instantiate the map against which we want to simulate the agents, and also to a motion generation, which places the agents on the map and then simulates the behavior of these agents for the next 5 seconds. Crucially, with this framework, we can seamlessly use outside sources of information, like, for example, crash reports, police reports. So, for example, what we've done is to parse the NHTSA Siren database that contains many police reports of crash accidents that have actually happened, and then use the LCT Gen pipeline to recreate those scenarios in simulation with a little bit of generative AI on top to recreate those assets that are missing in a police report. A police report is just, a script by a police officer. So this is exciting for us because it directly addresses one of the key challenges in simulation, that of generating stress testing scenarios that are yet plausible. It's very easy to generate adversarial scenarios, but at the same time, you want to do that in a way that is plausible, not to expose the policy under test or autonomy stack under test to scenarios that are unrealistic and thereby not informative. Now, one problem with the LCT Gen is that it's still finicky to just describe with words precise geometric information, like, for example, where you would like the agents to specifically be in a scene. So in more recent work, referred to as a ProSim, we have developed a model that is much more flexibly promptable. For example, with the ProSim, we can use as a conditioning inputs geometric goal condition points, trajectory sketches, discrete actions, and text conditioning, as I said before. So this makes it quite seamless for users to generate multiple different scene rollouts just by changing a few prompts. So putting everything together, we can now combine scene reconstruction pipelines with the capability of generating target scenarios through language guidance to simultaneously simulate a sensor and human agent behaviors in novel, targeted ways. For example, here we can test an AV stack on a long-tail scenario whereby a vehicle doesn't stop at the stop sign, basically emulating a driver that is inattentive. On the top row, we have the video that was actually recorded in the real world. And here we see that there is the vehicle within the green bounding box that is stopping at the stop sign as it should. And then by using our LCT Gen plus reconstruction pipeline, we can recreate the same scenario by telling the AI system to remove that vehicle, replace it back in the scene, and telling the simulator to create a crazy scenario where the vehicle doesn't stop at the stop sign. So the scenario at the bottom never happened in the real time, has been completely synthesized in simulation through the LCT Gen Plus neural reconstruction pipeline. Okay? So while this capability is great, there is still a fundamental caveat that applies to all neural reconstruction approaches. We need to already have collected the data from the target environment in order to reconstruct a given scene. A reconstruction pipeline reconstructs stuff that has been seen in the real world. And so this is a challenge because, of course, we cannot have a coverage for all possible scenarios we may be interested in. And to illustrate one of the pitfalls of reconstruction, let me show you a video from one of the traces from our own neural reconstruction simulator at NVIDIA. You see that now we're making a U-turn. That is a maneuver that is very different from the one that was used in order to record the drive that was reconstructed. And immediately you see a mess of artifacts that start popping up. Actually, it's a minor miracle that the policy is still working fine in this case. But we now live in the era of video generation models or video foundation models. You might have heard of Sora from OpenAI, Cosmos from NVIDIA. So it's tempting to say, well, we can then replace a neural reconstruction pipeline with a video generation pipeline and use that for simulation. So video generation or video foundation model can generate videos on demand for all crazy scenarios that you can think of. But as you may know, video generation models still suffer from possible hallucinations or lack of physics realism. So in recent work that is going to be presented here at the ICRA called the Dream Drive, we're trying to see whether we can combine these two branches, neural reconstruction and the video generation, into a single framework that tries to get the best of both worlds. The geometric accuracy of a neural reconstruction pipeline with the generation capabilities of a video generation model. And the way that the Dream Drive pipeline works is as follows. We start from an initial frame, in this case, a street view image from Tokyo, Japan. Then we use a video foundation model to generate a video from that initial frame that moves through the environment. Interestingly, you see an artifact there. So basically, you can see how the grass highlighted at the top changes color erratically from brown to green. This is, of course, an hallucination. A grass shouldn't change color in a matter of a few seconds. Well, this video is then fed into a neural reconstruction method to produce a 4D spatio-temporal representation of the environment. And finally, the ego vehicle is placed into this world and drives through it in a closed loop. Importantly, we ensure grounding and realism in two ways. First, we condition video generation with a real image. Okay, that's the easy part. But second, and most importantly, we ensure geometric consistency by reconstructing a single 4D representation through a reconstruction pipeline. And you can use different reconstruction pipelines. Here we use a Storm, which is our latest work that has been recently presented at ICRA. So this is the full pipeline, 4 steps. We start from initial image. We generate a video out of that image. We then build a 4D representation of it, and then we drive within it. And now you can see that the artifact whereby the grass, for example, was turning from brown to green is fixed through the geometric consistency that is brought about by a reconstruction pipeline. So I'm quite excited about this direction because, in a way, brings together two important branches, neural reconstruction and video generation, into a single formalism, again, basically getting the best of both worlds. There are other ways, of course, to bring together these two techniques. And I think that in the next year or so, there will be many other results similar, at least in this vein. Now, overall, these works bring us closer to a closed-loop simulation that we can use to evaluate models, as I said, both in terms of sensor realism, in terms of behavior realism, generalization, and so on and so forth. So this is great because now we can use closed-loop simulation, for example, to characterize potential compounding errors given the autonomy policy and so on and so forth. But closed-loop simulation has still its own disadvantages. For one, is computationally quite intensive. And this is the reason why open loop evaluation is still widely used, at least in a production context. The use of already collected real-world trajectories ensures computational efficiency. But with open loop evaluation, we now lose the availability, for example, of characterizing compounding errors that a given decision-making policy might encounter when being rolled out. So this initially appears to be a sort of a dichotomy. But we have viewed simulations as sort of a continuum spectrum whereby open loop simulation and closed loop simulation are at the ends of this spectrum. So the question is, can we devise an approach that somehow lands in the middle and thread a good balance between closed loop and open loop simulation? So in a very recent work that we're going to publish on arXiv in the next couple of weeks that we refer to as a pseudo closed loop simulation, that's exactly what we do. And the idea is relatively simple, but seems to be quite straightforward. So for each initial state within a data set, highlighted here with the orange box, we pre-compute future possible states that a given driving policy might end up with. And these future states are depicted in purple here. And then we render the views that the ego vehicle will see from there. So this is pre-computed. Then online, we roll out the policy being evaluated from that initial state to produce a final position that is highlighted here in green. In addition, we also roll out for the pre-computed purple endpoints the policy to obtain a second set of endpoints, here highlighted in light blue. The key insight and reason why we do this is that in such a multi-stage rollout, so this is akin to a sequential rollout from a policy operating in closed loop without requiring the computational overhead of rendering the intermediate stages, because all of those have been rendered offline. So how do we bring together then the information from all these different rollouts? Well, this is reflected in how we compute the final metric. We compute a distance-weighted average among the second stage rollouts depending on the similarity to the first stage rollout. And this is what ties together the policy initial rollout that ends into the green box with the policy secondary rollouts that ends in the purple boxes. So long story short, we found that such a pseudo closed loop simulation approach correlated much better with the closed loop metrics than their open loop counterparts by a significant margin. So this is interesting because now we have a tool that, as I said before, kind of thread the needle between a closed loop and an open loop simulation, and it can be used flexibly, for example, to add additional data, for example, for evaluation or for training or potentially for validation. Okay, I talked about validation. So validation, simulation for validation is an interesting topic. Indeed, safety in general is a very interesting topic for me and of course for the community as well. As you know, NVIDIA is investing heavily in developing safety frameworks and comprises both hardware and software. Jensen Huang, the CEO of NVIDIA, announced a program at the GDC called NVIDIA Halos that is targeting physical AI safety, and that brings under the same umbrella a number of research results from my group. And within this umbrella, one topic that I'd like to discuss before wrapping up my talk is that of using a simulator for validation. Oftentimes people talk about simulation for validation without realizing that that is very challenging for a very simple reason, that in general, when we use a simulation for either testing or training, we're interested in directional information. We're interested if a given policy behaves better than another policy. The specific numbers are not too important. If we want to use simulation for validation, then we are interested in the absolute values of those metrics, like, for example, mean time between failures and other related metrics. So then the question is, can we devise a simulator that is so accurate and we have so much confidence in it that we can actually take those absolute values at face value? So this is, of course, very hard. It goes down to the question of how good is good enough. But second of all, even if I developed a simulator that I really trust in order to assess the safety of a given policy, it is not the case that that simulator could be similarly trustworthy for another policy, because another policy might be actually affected by different type of inputs that have not been validated yet by the simulator. So in our work, we are actually turning to a more pragmatic question, that is that of how do we best leverage paired real-world and simulated data in order to reduce the number of real-world data that is needed to validate a system. And for that, we turn to variance reduction techniques. So just to keep the equation grounded, of course, validation encompasses several different axes, but for the purposes of this discussion, we focus on estimating the average of some metric of interest, which we call F. Like, for example, could be related to time to collision metric or something else, your safety metric of interest that you would like to assess in closed loop. So traditionally what you do is that you gather a bunch of samples from the real world, and then you have an empirical estimate of these random variable F according to a Monte Carlo estimate. So you sum all those samples and you take the arithmetic mean. And the variance of such a Monte Carlo estimate is the variance of the random variable F divided by the number of samples. We can't control the variance of F, it is what it is. So in order to reduce our uncertainty, we take as many samples as possible. But those are very costly to acquire because they come from real-world data or maybe from a very expensive closed-loop simulator. So to do better, as anticipated, we can turn to smart variance reduction techniques. In particular, we look at the tool of control variates. A control variate is a correlated signal whose expectation is known, for which we can measure, on each sample in addition to the metric of interest. Then we can estimate the true mean of F by taking the empirical mean of the difference between F and G and using a known expectation of G to correct the result. Of course, if you take the expectation of that quantity, you still get the expectation of F as a result. But what's the difference here is now that formula comprises the expectation of G, which is a known quantity with zero variance. And then there is a stochastic quantity that is the difference between F and G. But now I'm estimating through Monte Carlo a difference and not an absolute value, and that incurs much less variance. Intuitively, if F and G are correlated, the noise that is added to them cancel out. So mathematically, what that boils down to is that the variance of such an estimate is equal to the variance of our Monte Carlo estimator multiplied by 1 minus rho squared, where rho is the coefficient of correlation between the random variable F, the one we care about, and G, which is our surrogate, for example, information from a simulator. So of course, if rho is highly correlated, you dramatically decrease the number of costly samples that you have to gather from the real world. So with all the simulation capabilities we discussed today, a reasonable question to ask is whether we can use simulation measurements as a control variant by essentially pairing each real-world test with a simulated test of the same policy on the reconstructed scenario. This is certainly tempting, but there is a challenge. And the challenge is that we don't know the expectation of G. We don't know the expectation of the surrogate metric on the simulator itself. But our solution here is to leverage additional sim-only measurement to estimate the expectation of G. And say that we have K samples, simulation-only samples that are not paired with real-world samples that we use to estimate this surrogate metric. Then if we do so, the reduction in the variance is given by the variance of F over N times something that is very close to before, but the correlation between the random variables F and G is multiplied by K over K plus N, where K is the number of simulation samples we use to estimate the average of the surrogate metric. But as K goes to infinity, and the idea is that the sampling from G is much, much cheaper, then we recover the same variance reduction factor of 1 minus rho squared, we had before. So if you have a simulator or another surrogate metric that is highly correlated with the metric of interest that you want to assess from the real world, then this result is very useful. But what if your simulator is not super well correlated with the metric F you're interested in? Well, there is something else that you can do. Specifically, what we have explored is whether we can take your surrogate metric, like for example, average displacement error from an open loop simulation, and then transform it in a new surrogate metric that is designed to be better correlated with the metric that you are interested into. And to do that, what we do is to also leverage foundation model features. That's where, again, foundation models come to the rescue, to map a given surrogate metric, for example, average displacement error from open loop simulation, and foundation model features in a new surrogate metric that is trained on data that was acquired, for example, from previous validation processes. And we can see that from the two plots on the right-hand side, with this transformation, we can get metrics, surrogate metrics, and real-world metrics that are much better correlated. Why do we use foundation model features to boost this transformation of the surrogate metric into something that is better correlated? Well, the problem is that in order to synthesize this new surrogate metric, we are consuming some of the paired data. So we have less paired data that we can use for our variant reduction procedure. So ideally, we would like to use as least data as possible. And we actually see that by using foundation model features, we dramatically reduce the number of data that is needed in order to learn this metric correlator function. For example, on the plot here on the left, I show that we can already boost the correlation significantly with just a very tiny fraction of paired real world and simulation data. So in conclusion, what we're able to show is essentially this plot that is kind of interesting, and let me discuss it with you. So here we are in a scenario where we have about 500 paired samples. So basically scenarios in simulation that are paired with those that are reconstructed in scenarios in the real life that are paired with those reconstructed in simulation, and about 1,300 simulation-only scenarios. And we see that with our control variant technique, we can reduce the variance in our estimation by about 24%. And if on top of it, we use a better surrogate metric computed through the metric correlator function, we can reduce the variance by an additional 32%. And if I can simulate even more, I can have even greater variance reduction. So long story short, for a given confidence level in the metric that we want to estimate, we can get away, in this case, with about half of the real-world samples. And this is what was for a metric that is very bad, which is basically average displacement error in open loop. So for something that is much better, you might have even more dramatic reductions in the number of samples that you need. So it's very important for us because, especially in an era where we want to develop end-to-end driving policies that cannot be validated anymore open loop. So we don't have like KPIs for your object detector. We do have KPIs for your full end-to-end policy. You will need to validate this end-to-end policy every time with real-world data that is very expensive. So this type of variance reduction techniques or cleverer ways of leveraging a simulation for validation are going, in my opinion, to become very important in the future. So I will stop it here. Very quickly, foundation models provide a lot of opportunities to accelerate the development process in many different ways, from offline processes such as simulation all the way to the onboard stack, even though we haven't talked about the onboard stack today. I view simulations as a continuum between open loop and closed loop simulation, and we are investigating ways where we can thread the balance between the two. And finally, a topic that has been somewhat overlooked so far is that of how we can use simulation for validation. And we looked at ways to basically blend together data from the real world and simulation in a way that dramatically reduced the amount of real world data needed in order to compute a given metric at a desired level of confidence. So with that, I'll stop it here, and I'll be happy to address any questions you might have.
Thank you very much for the interesting talk. I was wondering, when you're doing the safety or using the simulations as safety validations, do you have any approach to how do you verify that the simulation you have is actually adequate enough to model the real world?
Yeah, that's the entire point, that it's very hard to validate a simulator. And even if you do it for a given policy, that validation argument may not apply to another policy because it might affect or rely on inputs that were not validated or assessed for the previous validation process, right? So that's why we don't place an assumption on how good the simulator is. In our more pragmatic view, we just try to pair data from a simulation and the real world. And simulation, the real world, will have some correlation. Rho, if the simulator is very good, rho is very high. If the simulator is very bad, the rho is very low. What that turns out into is that if the simulator is very bad, you will need more real-world samples. And if it is very good, you need less real-world samples. But we never place a burden on validating the simulator. If you have a better simulator, you just need less samples, and that is captured by the formulas that I show into the slide. So that's an excellent point. And actually, that was the motivation for this work.
Is there any numbers on what is good and what is bad?
So that is a bit tricky because it depends a lot on the product you are working with. So if you're working on L2++ hands-on, you have different numbers that if you're working with L2++ hands-off, and they're different than if you work on L3, and of course very much different than if you work on L4. And on top of it, it depends heavily on the correlation between the simulator and the real world. Interesting, and I haven't shown the results here, for our internal at NVIDIA neural reconstruction-based simulator, the correlation was so good that we didn't need to apply the metric correlator function trick that I explained here. And so I would expect practically a decrease in terms of hours of real-world driving that you need to accrue for validation to be cut from half to maybe another magnitude. But of course, depends a lot on the specific automotive product you're targeting.
Thanks a lot.
Yeah.
For the sake of time, really quick question. Yes. Just one.
Like in the start of the presentation, you had mentioned that your data is unlabeled and the model learns the physics in a self-supervised manner. So I was just wondering, like, is it generalizable, like in physics-defined simulators, when you change the mass of an object, its behavior changes? So if there is no data of a specific object with a heavy, like out of distribution mass or something.
No, because that was a reconstruction pipeline. So basically, it learns in a self-supervising fashion, but with respect to the scenes that are being reconstructed. If you want to generalize further, then you would need to use techniques, for example, from video generation models, and there how to constrain the generation in a way that is physically accurate is still an open problem in the state of the art.
But then in this case, like you had mentioned for accident training, like we don't have enough data for
accident training, yeah. Mm-hmm.
So like the physics also would be like less learned because there isn't enough data. So would the simulation still be accurate in that scenario?
Yeah, so that motivated actually the Dream Drive work that I presented, where we use video generation model to give, to have more generalization to entirely new scenarios, but then we corrected, if you will, post facto with a 4D reconstruction pipeline to then bring back some level of physics realism. Now, it's not going to be perfect, but definitely better than what you would have out of a straight video generation model.
Thank you.